Swayam Prabha. Digital India. Educated India.
Hello everyone. Now today's topic is the ballistic or impact principle of tensile characteristics testing. So apart from the static or quasi-static testing, like when we test the tensile characteristics of a textile material at slower speed, so that it's called quasi-static principle. The characteristics of the material will be entirely different when we apply one impact force, and the impact force is applied on textile material in many of the applications, like in bulletproof clothing or mountaineering rope. So there are many applications, or maybe parachute, where sudden impact force is applied. So it's important to test the impact testing characteristics of textile material. So here in tensile testing, we measure the tensile load or breaking load, but in case of impact testing, we measure always work of rupture. So work of rupture is also measured in case of quasi-static method, but in impact principle we measure the work of rupture, like energy to break or energy to rupture the material. So this is the schematic diagram of the principle. It works in pendulum principle. So first let us see the animation here, then we will discuss in detail. So first let us swing the pendulum. So a pendulum is there, which we are now bringing it to horizontal position. Okay, and here it's assumed that there is no frictional loss or no air drag. So with that assumption, when we release the pendulum from the horizontal position, it is swinging, and it will swing up to the horizontal position at the other end. So what is happening here, when pendulum is brought to the horizontal position, that means it's the potential energy is being stored in the pendulum, and then when we release, that potential energy is converted to that dynamic energy, that is kinetic energy, and then the energy is being utilized. Now try to see again the pendulum with the specimen. Here again we are swinging the pendulum towards the horizontal position, and in this case the thread or the specimen is attached with the pendulum, and other end of the thread is attached to a fixed jaw J1. Okay. Now the pendulum will be released. Now the pendulum, let us release the pendulum. Now pendulum is being released and now it is swinging. When it will come to the starting point, that is vertical position, the thread will be straightened, and after that the load will be on the thread, and there will be some energy required to break the thread or break the textile material, and this energy is being used to reduce the movement of the swinging of pendulum. Now initially the pendulum started from height h1. Now after losing the energy to rupture the material, the pendulum is reaching up to height h2. So this difference in height is h1 minus h2. So if the weight of the pendulum is W, then the energy required to rupture the material will be W multiplied by h1 minus h2, where h1 is the initial height and h2 is the height, maximum height reached up to after the rupture of the material. So here you can see h2 is the height and W is the weight of pendulum. So potential energy at the starting point 1, when we are swinging the pendulum to its initial position, that is 1 in the horizontal position, and W is the weight of pendulum and h1 is the height. So W h1 is the initial potential energy, and when it's released it swings down and reaching to its initial point 2, where the potential energy is minimum. It's a rest position, and then it will swing further and reach to the point 3 as we have seen. So work of rupture is h1 minus h2 multiplied by W. It's a weight. Now here one thing we should see, that the point where the thread is attached or the jaw is attached need not be the center of gravity. It will be somewhere else. So this point is known as the, say K, this point is known as point of percussion, and point of percussion we can just get the understanding of point of percussion, that in while playing playing cricket, this is the cricket bat, and when the batsman hits the ball, and it can hit at any point, there will be one point in the bat, total area of the bat, where when batsman hit, the jerk, that the jerk will be minimum. So this point is called sweet point or point of percussion. Then why this point is important? This point is important because if we attach the jaw in any other point, what will happen? During the impact, the pendulum will start random swing, random some vibration will be there. So to eliminate this problem, so we use the point of percussion where the reaction force is minimum. So all the energy is used to rupture the specimen. Otherwise, part of the energy will be used for the random motion of the pendulum bob. So after breakage, so the pendulum will swing without any disturbance. So this point K here is known as center of percussion. Okay? It's not the center of gravity. Now let us try to solve few problems. Now total weight and initial height of the pendulum bob of a ballistic tensile tester are 25 Newton and 1 meter. Initial height is 1 meter respectively. If the work of rupture of the specimen tested is 15 Newton meter, then the total swing angle of the pendulum during its travel, that we have to calculate, total swing angle. So this is the pendulum, and we are initial position of the pendulum is 0.1. This is the initial position, and it's swinging up to a certain height. That is height. Initial height was h1, and after rupture the height has become h2, where h1 is more than h2 definitely, and we can calculate the work of rupture. Now what is being asked here? To calculate the total swing. This is the total swing during the rupture. So total swing angle of the pendulum. So the work of rupture, we know, weight of pendulum h1 minus h2. So initial height was 1 meter. Okay, and the initial height h1 is 1 meter, and the total weight of the pendulum, so W is 25 Newton and this is energy is 15 Newton meter. Okay. Now what we will do, we will try to calculate H2. H1 is given, so 25 multiplied by 1 minus H2 equal to 50. Okay, so H2 is in meter. So if you 1 minus H2 equal to 15 by 25, so H2 will be 1 minus 15 by 25. So 1 minus 15 by 25 becomes 0.6. So it will be 0.4. So 0.4 meters. So it is reaching up to height 0.4. So 0.4 is the final height, and that means if we see this is the point, the vertical height is, this height is 0.6, that is A, so B point, this is a B point, so AB is 0.6, so this is 0.6 and we know the, say, ABC, ABC, the C is the total length of the pendulum rod. So AC is the initial height, AC will be H1 is 1 meter. So this is 1 meter. So we can calculate this angle phi. This is the angle we can calculate. So let us see. So H1, H2 are the initial and final height. So weight of the pendulum bob is 25 Newton. So we can calculate H is 1 meter, and from this relationship we have calculated H2 is 0.6, that we have already calculated. H2 is 0.4 meter. We have already seen the maximum angle of swing to the left side of the vertical position of the pendulum is theta. So here, so cos theta equal to 0.6, that we have seen. Here this is theta. Okay, we can see, we can call it as phi. So otherwise we will get confused. So this is become, this is not theta, this will be phi. So cos phi will be that's 0.4 by 1. Okay, sorry, now this is H2 is H2 is 0.4, this is 0.6. So cos phi will be 0.6 by 1. So phi we can calculate here. The phi value will be 53.13 degree. This is not theta, this will be phi as per the picture. Okay. Now total angle, swing angle will be 90 degree, because if we see the diagram, so we have calculated this phi, and total swing will be 90 degree plus phi. So total swing angle, say if we see theta, 90 degree plus phi. Okay. So total swing angle will be 143.13. So in this way we can calculate the total travel of the pendulum. Next one, the total weight and the initial height of the pendulum bob in a ballistic impact tensile, actually pendulum principle, is 14 Newton and 0.5 meter respectively. If the final height reached by the pendulum bob after the breakage of the specimen is 20 centimeters. Okay. So initial height H1 is 0.5 meter. Height reached after breakage is 0.2 meter, and weight is 14 Newton. So what we have to calculate? The work of rupture. It's a simple. So work of rupture will be W multiplied by H1 minus H2. 14 multiplied by 0.5 minus 0.2, 14 multiplied by 0.3 Newton meter. So the value will be 4.2 Newton meter. So in this way we can calculate the work of rupture. So work of rupture we have seen. H1, H2 we have to calculate. It's a given, so we have to calculate the work of rupture. So W is 14 Newton and H1 0.5 and H2 0.2. So we will calculate the work of rupture as 4.2 Newton meter. So this behavior of tensile behavior in quasi-static tensile strength and the impact tensile strength are entirely different. Okay. So that, and here impact type tensile strength is important for many applications. Another numerical, total weight and initial height of the pendulum bob are given 40 Newton and 0.8 meter. Work of rupture is given 30 Newton meter. The total swing angle, again we have to solve the numerical. Here initial position, which is horizontal position, and here the rest position, and it has reached up to certain height. So this is the final position, 1, 2 and 3. Okay, and it has reached up to this height h2. So initial height h1 is given 0.8 meter and the weight is 40 Newton. Okay, now the work of rupture 30 Newton meter. So we can write the equation 40 W multiplied by this H1 is 0.8 meter. So H1 minus H2 equal to 30 Newton. 40 multiplied by 0.8 minus H2 equal to 30. So 0.8 minus H2 equal to 30 by 40. It will become 0.75. Okay. Now from here we can calculate the H2 will be 0.8 minus 0.75. It will be 0.05 meter. Okay, this is 0. So H2 will be 0.05 meter, and that means this height from point O, original point, pivot point, to this, here is this height will be 0.75, and the swinging beyond the vertical position you can term it as phi, and the length of the pendulum is 0.8. So we can calculate the cos theta, cos phi will be 0.75 by 0.8. So it will become, cos phi will be 0.75 by 0.8. It will become 0.71. So phi we can calculate cos inverse 0.71, that we will get certain value. So let us see the solution here. So work of rupture is given. So initial height and final height H1, H2, and weight of pendulum. So from there we can calculate the final height, which is 0.75. Okay, and the H2 is 0.05 meter as we have calculated, and maximum angle of swinging to the left side of the vertical position, here say theta is the maximum swinging angle. So cos theta is 0.75 by 0.8, 0.937. So I think we have made some mistake. So this is becoming 9.937. Okay, 0.9. So theta will be 20.75 degree. So total swinging angle will be 90 degree plus 20.75. Okay, 90 degree plus 20.75 is 110.75. So here 90 plus 20.75, so 110.75 degree. That is the total swing. Now our next numerical is again the total weight and initial height is given. So total weight is 20 Newton and initial height is 50 centimeter. Final height of the pendulum reached is given 18 centimeter. Then one work of rupture. It's straightforward. Work of rupture will be N multiplied by H1 minus H2. So 20 multiplied by 50 minus 18, 20 multiplied by 32, 640. This is Newton centimeter. And if we want to calculate the Newton meter, so it will be 6.4 Newton meter. So you must be careful of unit conversion. Okay. So this is done. So 50 and 0.5 meter and 0.18 meter and 6.4 Newton meter is the work of rupture that we have calculated. Next numerical. So that here you can see, in this case if we want to calculate the angle swing, total swinging angle, so this is the, you can see here, this is the height, initial height is 20 and if the final height of the it's reached, my initial height is 50 and final height is 18. So this distance will be 32 and here the length of the pendulum is 50. So cos phi will be the angle beyond the vertical line, say phi, cos phi will be 32 by 50, 0.64. So here cos inverse 0.64. Okay, so this is the angle we can calculate here, and the total angle will be total swing will be 90 degree plus 5. That we can calculate. Now the next principle is the strain gauge principle. It's transducer principle, and this principle is used widely in most of the modern tensile testers. And not only in tensile tester, the transducer principle, strain gauge principle is used in weighing balance. Okay, here the process is that there will be a beam, and due to the load applied, the beam will little bit bend. This bending is negligible as compared to the extension of the material. So in that case, that's why we consider this principle as constant rate of elongation, because this lower jaw is moving at constant rate. Although there will be deflection, still we don't consider this principle as constant rate of traverse. We consider it constant rate of elongation, because the deflection of the beam or the movement of the upper jaw J1 is negligible, and it works on Wheatstone bridge principle. The principle is that in this beam, when the beam bends, the length of the upper face AB which extends, that is the principle, and the lower face CD which contracts. Okay, but at the center in L, which is a neutral zone, so the length doesn't change at the center. Okay, above the central line, the beam get extended, and below the central line, the beam get contracted. So the Wheatstone bridge is being formed. At the top, two resistance wires are fitted, and at the bottom surface, two other are fitted. Now, while applying load, the top portion will get extended, so this resistance wire will also get extended, and the resistance wires which are fitted at the bottom, they will get contracted. So initially, when there is no load, that is the length of this resistance wire are at its normal position, normal condition, the output voltage will be 0. Okay, but when the load is being applied and the resistance wire are extended or contracted, so it will, depending on the extension and contraction, the system will generate some output signal. So based on this voltage generated, this voltage is a function of the force. So this voltage is measured, but we are indirectly getting the force value. So this is the principle. The main advantage of this system is that we can develop instruments which are very, very sensitive for microbalance, where we measure very low mass to the very high capacity weight. So the loading can be of wide range. So in this type of system, we can test fine fiber tensile test. We can perform for a fine fiber as well as for a very thick rope. So how to convert this value of change in resistance to load applied on the specimen. So when we apply, suppose we apply certain load L1, okay, and using this Wheatstone bridge we get certain voltage V1. Similarly, we keep on changing, increasing L2 we get V2, L3 we get V3. So using this data we will get one regression equation, and this regression equation will be used for predicting the load value for a given voltage value. So two resistance wires are placed on the upper surface, and two are on the lower surface. And to form a Wheatstone bridge, so these are forming Wheatstone bridge. So with the beam undeflected, no voltage across the output CD. There won't be any voltage across CD. So that's why it will be called balanced condition. So any voltage applied across AB, so there will be no voltage across CD. When the load is applied, the deflection occurs and the values of the resistance changes due to the change in their length. So voltage is produced across the CD, and this is proportional to the load as I have discussed. So initially the calibration needs to be done to form a regression equation. So the main advantages are free from inertia error. Okay, like in other system when we have discussed the pendulum type system or maybe beam balance system or impact type system, there the inertia error should be there. There will be some inertia error. We cannot actually eliminate all the inertia errors, but here as it is quasi-static method, so there is no inertia error. So deflection of the end of the beam is very small, and thus it is tested under CRE condition. And it's versatile type instrument. So yarn, fiber, fabric, and wide speed and wide range. So everything can be incorporated within this type of principle. So that's why this instrument is called UTM, Universal Testing Machine. So wide range of material can be tested. And main disadvantage is that this is very sophisticated one and needs expert technician, and chances of drift is there, drift in electronic circuit. So after repeated extension and contraction, the resistance wire sometimes give wrong results, so permanent deformation is there. So that may result the wrong reading. So frequent calibration is required. So at regular interval. Cost will be high. Now, another principle is constant tension winding test. So this instrument is extremely important for textile processes like winding, warping, sizing, where the yarn moves at constant speed, at certain speed, under certain tension. Okay. Suppose we have two yarns, yarn 1, yarn 2. Mean strength of the yarn 1 is say 50 and mean strength of the yarn 2 is say 40. Number of breakages per 1000 yard, here say 5, here 2 breakages are there. Now which yarn will be suitable for winding or warping or even weaving? So sizing, so all the running condition. So in the running condition, the breakages of the yarn 1, although it has got mean strength higher strength than the yarn 2, but still this will perform poorly during the winding or warping. So because the number of breakages will be more and the efficiency of the running will be reduced and it will generate some additional defects. So the constant tension winding test will identify the number of breakages. The principle here is that the yarn is moving through a guide rollers A and B, and some load is being applied on the yarn. So L is the load applied and Vx is the input speed and Vt is the output speed. This is the condition. So this system provides conditions somewhere similar to the actual processing of yarn during winding warping size. So where the yarns move, so the test is closer to the actual running condition. So as I have told that yarn may be very strong, but depending on the weak point during the running, it may break. So this system predict the weak points also. So AB are the fixed pulleys and P movable pulley which applies the load under static condition. The tension of the loop will be 0.5 L because it's this total load is being shared by two sides, uniform throughout the loop, and output speed will be input speed multiplied by 1 by E. E is the extensibility of the material. So if we know the extensibility at a certain tension, so that we can adjust the output speeds. Okay. So necessary means are required to adjust the input and output velocity. So the standard way of expression is that the tension required for 8 breaks per 1000, that is the standard. So what we do, we try to increase the tension, that is load, we try to increase till the breakage rate reaches 8 breaks per 1000 year. That is the tension, standard tension. So if the tension value is high, that is dynamic tension is high, that means the yarn is better. So higher tension is required for 8 breaks per 1000 yarn. So yarn 1, so this is yarn 1 and yarn 2. Okay, yarn 1 at say 10 Newton load, when we are running a 10 Newton load, yarn 1 is giving the breakage rate of say 5 breaks per 1000 yarn. Yarn 2 gives say 20 breaks per 1000 yarn. Okay. Now for yarn 1 to bring it to 8 breaks per 1000 yard, we have to increase the load. So say at 12 Newton it becomes 8 breaks. But for yarn 2 to bring down the breakage rate to 8, so we may have to reduce the load to say 4 Newton. 4 Newton, it becomes 8 breaks per 1000 yarn. So we will compare the 4 with 12. 4 and 12 is being compared. So yarn 1's dynamic tension is 12 Newton. Yarn 2, the dynamic tension is 4 Newton. So yarn 1 is better than yarn 2. In this way we will express. So standard breakage rate is 8 breaks per 1000. Okay. The tension required T to get the standard breakage rate is measured as we have discussed. So for yarn 1 and yarn 2, that we have discussed with that example. Now during the winding, the nature of breakage is that breakage running tension and breakage rate, they are related in this fashion, straight line fashion, where with the increase in tension, the breakage increases with logarithmic proportion. So if we take the y-axis as breakage, log of breakage, number of breakage per unit length, and x-axis is the tension, so they will be related as a straight line, where the slope of the line can be calculated. The slope of this line will be for say point n1 and n2. The slope of the line will be from T1. So for tension T1, the number of breakage per unit length is the n1, unit running length n1. So and T2 is that for at T2 tension, the breakage rate will be n2. Okay, and from there we can calculate the slope. This is the slope tan theta. So tan theta, the angle of inclination is theta. Tan theta will be this distance. What is this distance? That is log n2 minus log n1. This is the distance divided by this distance, that is T2 minus T1. This is the slope of the curve. Okay. Which is constant for any point. So if we get the breakage rate at 2 points, so for T1 and T2, the breakage rates are N1 and N2. In that case, we can calculate the breakage rate at any tension T, okay, using the equation. So if the tension T required to produce X breaks per 1000 yard, then we can calculate the tension required T by the simple formula. This is a simple formula, which is T equal to T1 plus T2 minus T1. Log X is the number of breakage at tension T, log N1, and log N2 minus log N1. Okay. So we have calculated the tension required T to have certain breakage rate and vice versa. So we can calculate the breakage rate at certain unknown tension. And also, if we want to achieve certain breakage rate, we can predict the tension required. So suppose we want to achieve a breakage rate of half of N1. So log N1 by 2. If this is the point, then we can calculate the tension required. So breakage rate, applied tension, and single set strength. The empirical equation is This is the empirical equation where the static single thread test, that is the quasi-static tensile testing, okay, and this is the mean tensile test, tensile strength x bar. T is the tension required to produce n breakage per 1000 yard, and static mode mean single ion strength, that is x bar. X bar is the mean single ion strength in static mode, and sigma is the standard deviation of single ion strength. So dynamic strength and static strength are related by this relationship, where sigma is the variability of the single ion strength. So here from this equation we can simply see, for a, say this is a certain strong ion, but if the variability is more, so standard deviation is more, that means even the ion is strong, the tension required to have certain breaks per unit length will be lower. So variability is also important. So K is a constant, it's a factor, depends on n number of breaks, and also it changes with the test length of single ion tensile test. So if the breakage, number of breakages changes, n changes, so K value will change, and also if the tensile tested, the test length, if the gauge length changes, this K value will also change. But for a certain condition, certain standard condition, the K value is constant. So as per British standard PS, this standard is 3.3. K value is equal to 3.3. What is the condition? In PS handbook, the first estimate of tension required to produce n 8 breaks per 1000 yards. So it depends on the n. So n 8 break per 1000 yards, and the test length is 20 inch. If the test length is 20 inch and if it produces 8 breaks per 1000 yard, then the relationship will be, this relationship will be there, where T tension required equal to average single ion strength, static strength, multiplied by 1 minus Cb of single ion strength by 330. By rearranging this equation, we get x bar minus 3.3 sigma. Sigma is standard deviation. So this is nothing but this constant K. So this constant we are getting only in this condition, 8 breaks per 1000 yard, and here the gauge length is 20 inch. So K equal to 3.33 with 20 inch test length and 8 breaks per 1000. At that condition only it will be 3.3. Okay. But for other conditions, when breakage rate changes and gauge length changes, we can calculate the K value. For our numerical, we don't have any other value with us. So to use this equation, we have to first get the K value 3.3, because this is the known value, and to use the K as a 3.3, we have to bring our conditions to N equal to 8 breaks per 1000 yard and gauge length is 20. So in this condition, if it matches, then only we can use K as 3.3. That we will discuss, okay, through the numerical. Now let us see the example. Now, during cone winding of yarn, the breakage per kilometer, so break per 1000 meter was observed 40. Cone winding breakage per kilometer of yarn was observed to be 40 and 60 at winding tension of 250 centinewton and 40 centinewton. So N1 is 40, N2 is 60. So break per 1000 meter, this is break per 1000 meter, and T1 is 250 centinewton and T2 is 450 centinewton. These are the conditions given. The expected number of breaks per kilometer at winding tension, so T is given 500 centinewton and expected number of breakage per kilometer. So we will simply use the relationship we have discussed. So tension required T, the tension is given, T is 500 here, T1 250, T2 450, 250, log x is x we have to calculate, N1 is given 40, N2 is given 60 and N1 40. So if we solve this relationship, then we will get the value of T. T is known, so we will get the value of x. So tension required to achieve x breaks per 1000 yard, T1 and T2 are the tensions on which the tests were performed. N1, N2 are the breakage rate at tension T1 and T2 respectively. So N1 is given as we have discussed, T1 given, N2 60 and T2 450. We will use the relationship. So this is the relationship here, and after solving we will get this x. So log x equal to log 40 by log 60 minus log 40 equal to, so this goes here 250 divided by 200. So it will be 1.25, and we are just log 40 means 1.602, log 60 1.778. So from there we will be able to calculate the x. Log x becomes, so from this equation, so log x will be 0.22 plus 1.602. So log x will be 1.822. From there we can calculate x is 67. So 67 brakes per kilometer will be there at 500 centinewton load. So we'll stop here and we'll continue with the constant tension winding test related numerical. Thank you.